All right, let's dive right in. Today, we're getting to the very heart of modern electronics to understand one of its most critical components, the semiconductor diode. You can think of it as the ultimate gatekeeper. It's this tiny device that makes one simple but super important decision. Does electricity get to pass, or does it get stopped dead in its tracks? On the outside, it looks pretty simple, right? But what's happening inside, down at the atomic level, is actually incredible. This little component is essentially a smart, one-way valve for electricity, and in this explainer, we're going to pull back the curtain and see exactly what makes it tick. So that's the big question here, isn't it? How does this tiny, passive-looking thing make such an intelligent decision? How does it know which way to let the current flow and which way to block it? Well, that's the mystery we are about to solve. Okay, let's get into the physics of it. The secret to the diode's power, it all lies in how it's built. It all starts at this meeting point of two special materials, a boundary that we call the p-n junction. And as you'll see, this junction creates a kind of invisible wall that controls absolutely everything. So a diode is made by smashing together two types of specially treated semiconductor material. On one side, you've got the p-type region. It's got an abundance of what we call holes. Just think of them as these little positively charged parking spots waiting for an electron to pull in. On the other side is the n-type region, and it's just full of free-roaming negative electrons looking for a place to go. The p side is called the anode, and the n side is the cathode. And get this, the arrow in the circuit symbol, it's basically a little cheat sheet showing you the only direction conventional current is allowed to flow. Now here's where it gets really cool. The moment you bring these two materials together, those free electrons from the n side can't help themselves. They immediately rush over to fill the holes on the p side. This little migration creates a thin layer right at the junction that's now empty or depleted of any free-moving charges. We call this the depletion region, and it acts like an invisible wall. It sets up its own internal electric field, the barrier potential. Think of it as an energy hill that's just too steep for any other electrons to climb on their own. So we have this natural wall just sitting there, stopping the flow. How do we open the gate? Well, it's simple. We apply an external voltage. This process is called biasing, and it's basically how we tell the diode whether to let current through or to reinforce that wall and block it completely. And there are two ways we can do this, and they produce wildly different results. We can either connect our power source in forward bias, which basically encourages current to flow, or we can connect it in reverse bias, which reinforces the blockade. Let's break down how each one works. First up, forward bias. What we do here is connect the positive terminal of our battery to the p side, and the negative terminal to the n side. This external voltage directly pushes against the diode's own internal barrier, and the effect? It's like giving all the charges a running start. It shrinks that depletion region, and effectively, it lowers that energy hill, making it way easier to cross. And this right here shows the result perfectly. With that barrier lowered, the majority carriers, that's the electrons from the n side and the holes from the p side, they finally have enough energy to just flood across the junction. This creates a really significant diffusion current. We're talking a flow big enough to be measured in milliamps. That's thousands of an amp. The gate is officially open for business. Okay, so we know how to open the gate. That's pretty straightforward. But what happens if we flip the battery around? This is where the diode really shows us its incredible gatekeeping power. Let's talk reverse bias. Now, we connect the positive terminal to the n side and the negative to the p side. Instead of fighting that internal barrier, our external voltage is now helping it out. It basically pulls the charge carriers away from the junction, making that depletion region even wider, and that energy hill much, much steeper. The wall just got a whole lot higher. So with this massive wall in place, the majority carriers, they're completely blocked. No way through. But there is a tiny, tiny exception. A handful of what we call minority carriers. These are just stray electrons on the p side and stray holes on the n side. They get swept across by this powerful electric field. This creates a tiny trickle called drift current. And I mean, it is incredibly small. We're talking microamperes or millions of an amp. For all practical purposes, the gate is slammed shut. Okay, we've seen the physics at the atomic level, which is cool. But now let's look at the proof on a scale we can actually measure. We can plot all of this behavior on a graph that gives every diode its own unique signature, the VI characteristic curve. To actually get this curve, we use two slightly different test setups. For forward bias, since we're expecting a decent chunk of current, we use a milliamp meter.
But for reverse bias, the current is so minuscule we have to use a much more sensitive microammeter just to even see it. So by slowly cranking up the voltage and recording the current, we can map out the diode's exact behavior.
And here it is, that signature curve. Look at the forward region on the right. At first, almost nothing happens as we increase the voltage. But then, as we get close to what's called the threshold voltage, it's about 0.7 volts for a standard silicon diode, the current suddenly just shoots up exponentially. The floodgates open. Now look at the reverse region on the left. The current is practically zero. It's almost a perfectly flat line, showing that pretty much nothing is getting through, no matter how much reverse voltage we apply. Well, up until the point called breakdown voltage, where the diode basically fails. Now, here's a really crucial point. A diode's resistance isn't some fixed number like it is for a simple resistor. I mean, look at the graph. It's a curve, not a straight line. That tells us the resistance changes dramatically depending on the voltage. We can measure this at any given point on the curve using a concept called dynamic resistance. It's simply the ratio of a tiny change in voltage divided by the resulting tiny change in current. Let's actually put some real numbers to this to see how wild it is. Okay, in forward bias, up on that steep part of the curve, a tiny little 0.1 volt change causes a huge 10 milliamp current change. You do the math, delta V over delta I, and that's a resistance of just 10 ohms, basically a wide open gate. Now let's look at reverse bias. A massive 10 volt change barely moves the needle, just a 1 microamp change in current. That same math gives us a resistance of 10 million ohms. That is a sealed shut, reinforced wall. A million times. Let that sink in for a second. The resistance changes by a factor of a million, all depending on which way you point the voltage. Low resistance one way and an astronomically high resistance the other. This is the secret. This is the superpower of the diode. So what does this incredible one-way behavior actually let us do? This brings us to the diode's most important job in the entire world of electronics, creating one-way streets for electricity. So when you boil it all down, it's this simple. The diode is a one-way valve. You apply voltage in the forward direction, the valve opens and current flows freely. You apply voltage in the reverse direction, the valve slams shut and current is blocked. This amazing ability to convert the two-way alternating current, or AC, from our wall outlets into the one-way direct current, or DC, that all of our electronics actually need, that's called rectification. It is the absolute foundation of every single power supply you own. So let's just recap the whole journey real quick. A p-n junction naturally creates an energy barrier. If you apply a voltage one way, that's forward bias, you knock that barrier down, creating a low resistance path for current. If you apply it the other way, reverse bias, you build that barrier way up, creating a high resistance wall. And this simple, brilliant, one-way behavior is what lets this tiny component convert AC into the clean DC power that runs our entire digital world. So we've seen how a single diode acts like a simple one-way street. That just leaves us with a final thought to chew on. If one diode is a simple gatekeeper for traffic going one way, how could you arrange 4 of them to build a kind of intelligent intersection that could direct traffic efficiently no matter which direction it's coming from? Well, that's a puzzle for next time. Thanks for joining me.